Hello, everybody. So we're going to talk about Section 4 in Chapter 8, which is estimating the difference between two population means. Now, the idea behind this, the idea behind this chapter, or this section, I'm sorry, directly stems from what we've already learned about confidence intervals. It's just with sections 1, 2, and 3, we were specifically talking about, estimating, we'll just say mu, or the population parameter proportion P. But with this section, we're going to be able to look at, we're going to look at the comparison of two population means. So like, for example, let's say you are trying to compare the average class score of two classes. One class is during the day, one class is at night. And the professor, for some reason, in the morning uses traditional paper homework. However, at night, the professor decided to use online homework or adaptive learning homework, which is what you're using right now. Is there a significant difference between students' homework scores? And you can determine that based off the average score to see if there's a real difference or not. Another thing you could do is you can look at the average stem diameters of plants on two different types of nutrients. That's what your book says. So, for example, let's say you're using Miracle-Gro on one set of plants, and on another same type of plants, you're using a different type of nutrient-rich soil that has special additives in it, like Miracle-Gro, but it's a different brand. You want to see, is there a difference? Or maybe they're basically the same. It's just one of them is 3 times the price as the other. So what I'm going to do here, since we already have an idea about critical values and all that other stuff, I'm going to jump just right into the properties of the sampling distribution and the difference between two sample means. So let me go ahead and write this down. All right, so here are the properties of the sampling distribution, x bar 1 minus x bar 2, which is the difference between two sampled means. Now, there's going to be a lot of writing here, but the idea behind what we're doing in this section and what we did in the previous sections are the exact same. We're creating a confidence interval, but in this case, we're comparing the difference of two sample means, and we're trying to estimate the difference between their population means. So when independent random samples of N1 and N2 observations are selected from populations with means mu1 and mu2, and their variances, variance 1 and variance 2, respectively, the sampling distribution of the difference between the means has the following properties. Number 1, the mean of x bar 1 and x bar 2 is mu1 minus mu2, where the standard error is going to be equal to the square roots of the variance for sample 1, or population 1 divided by N1 plus the variance for population 2 divided by N2. Now, when the sample sizes are very large, remember, your sample standard deviation will turn into your population deviation as n goes to infinity. So when you have really large sample sizes, the difference between the variances from the sample to the population decrease. So we can say that the standard error is also equal to the square root of the sample variance over its sample size, the plus the the sample deviation or the sample variance over the second sample size. Now remember, this is for large values of n, okay? Or I need to be more specific, n1 and n2. Which leads us basically into the next two properties. All right, if the sampled populations are normally distributed, now that's going to be huge for us. So if we know that the samples that we obtained from our population are normally distributed, so that distribution is normal, then it doesn't matter how big the sample size is, because the difference between the sampling distributions is exactly normal, regardless of the sample size. So what that's saying here is this. If you got a population that you know is normally distributed, you could still use what we have above for the standard error for any sample size n, because we know it's normally distributed. However, with part number 3 here, if the sample populations are not normally distributed, all right, and that's different, then the sampling distribution x bar 1 minus x bar 2 will be approximately distributed as long as you have 30 or more samples for each population. Now, remember, we looked at the central limit theorem. That's what CLT stands for. The larger the sample size, even if it's not normally distributed, will start to turn into something that is normally distributed. It just depends on how bad your data was initially. Now, sometimes you just have bad data and there's nothing you can do with it. Other times, it may look slightly skewed, but if you just keep getting more samples, you're going to get something that is going to resemble a normal distribution. Now, we can figure out z-scores for the difference between two sample means by using the z-score formula, which is listed below. So z is going to equal the difference between the sample populations minus the difference between the populations themselves, all divided by the standard error, which is going to be the square root. Well, you see it right there. I don't want it gets confusing when I start saying variance 1 over n1 plus variance 2 over n2. It just gets repetitive. But you got the formula. This will give you the z-score. And then lastly, for large sample point estimation, so if we want to create a confidence interval, our best point estimate is going to be x bar 1 minus x bar 2. And remember, and this is in your book because I got a bunch of emails about this, okay? Where if they don't give you a confidence level, you assume 95%. Now, I'm not making that up at all. All right, it's not like it's just like a rule of thumb. It's in your book. Let me show you. So here's our book right here. I just want to show everybody this because if there's no stated confidence level, you assume 95% margin of error. Okay? So like I said, this is in our text. Sometimes though, it's easily overlooked, and I get that. I've read so many different stats books in my day that some of the books actually explicitly state this, like our book, versus others don't. So I'm just hoping to remind us here that if there's no confidence level listed, use 95%. Otherwise, they're going to tell you what they want, or I'm going to tell you what I want. All right, so our confidence interval is stated below. So we have the difference between x bar 1 and x bar 2 plus or minus our critical value. Now, we are familiar with some critical values, okay? So remember, I'm going to write it over here on the right-hand side. So if it's 95%, you're going to use 1.9. Oh, yeah, you're going to use 1.96 plus or minus. If it's 90%, you're going to use plus or minus 1.645. If it's 99%, you're going to use plus or minus 2.575. And if it's anything other than that, you're going to have to use your normal distribution table of z-scores and figure it out. Okay? But the main thing down here, all the way at the bottom of your page, is when we go to construct the interval. Right there's our lower limit. Here's our upper limit. So let me write them down. So there's our lower limit. Here's our upper limit in terms of the confidence interval. And what we are trying to estimate is directly in the middle, which is the difference of the population means. So I think we got enough information here. We can go directly into an example problem. All right, so here's our example right here. If you want to, just pause the video, write it down, and then you could follow along, or you could do the problem along with me. So the wearing qualities of two types of automobile tires were compared by road testing samples of N1, which equals N2, which equals 100 tires, for each type, and recording the number of miles until wear out, and the results are shown below. What we want to do is estimate the population mean difference in mean miles to wear out using a 99% confidence interval. And then we also want to answer the question, is there a difference in the average wearing quality for the two types of tires? So what's happening here is this. You may have two completely different brands of tires. Let's say Firestone tires and Goodyear tires. Our goal is to determine, is there a difference in quality when it comes to wear out between these two tires? So tire 1 had an average wear out of 26,400 miles with a variance of 1,440,000 miles. Tire 2 had an average wear out of 25,100 miles with a variance of 1,960,000. Okay? So our goal first is to create the confidence interval, and then 2, we're going to try to determine if there's an average wearing quality for the two types of tires. So the first thing we want to do, anytime you create a confidence interval, is let's go ahead and find our best point estimate. Now we know the best point estimate, in this case for mu1 minus mu2, is going to be x bar 1 minus x bar 2. So x bar 1 minus x bar 2 is going to equal 26,400 minus 25,100, which is going to equal 1,300 miles. So that's our best point estimate. Now we're going to find the standard error. So using the formula above, we know that the standard error is going to equal the square root of variance 1 over its sample size plus variance 2 over its sample size. So that's going to be the square root of 1,440,000 over 100 plus 1,960,000 over 100 as well. And if you do the math, the standard error will be 184.4 miles. Okay? Now, the 99% confidence interval, I'll abbreviate that as just CI, is going to be calculated to be the difference in sample means plus or minus the margin of error. Now, our margin of error here is going to be plus or minus 2.575 times 184.4. So I'm going to write everything directly beneath. We got 1,300 plus or minus 2.575 times 184.4, which gives us 1,300 plus or minus 475.8. And when we go ahead and just take 1,300 minus 475.8, we get 824.2, which is going to be less than our estimated parameter, mu1 minus mu2, which is going to be less than, well, now if we take 1,300 plus 475.8, we get 1,775.8 for our confidence interval. Now this is going to be our 99% confidence interval. Okay? And just to kind of summarize this, you know, I always like to write a little sentence here. We could just say that we are 99% confident that the difference in the average miles to wear out That's one word. For the two types of tires is estimated to lie between 824.2 miles and 1,775.8. All right. Now, that's our interval, but we need to answer the second question. So if you forgot what the second question is, I'm going to scroll up and I'll highlight it here for us. And here's our second question right here. Is there a difference in the average wearing quality for the two types of tires? Okay, so I think we can summarize that question a little bit easier, or we can comprehend that question a little bit more succinctly if we just explain what this question's what it's really asking, which is there a difference between these two tires? Is one tire a little bit better than the other in terms of average miles to wear out? So here's what we're looking at. If these two tires were the same, so if the tires were the same, in terms of, and I'm going to put this in parentheses, average miles to wear out. If they were the same, then the differences between mu1 and mu2, which I'm having a problem writing mu2, the differences between these two would be 0. They would have to be. In other words, if they were the same, then mu1 and mu2, using basic algebra here, the mathematics doesn't lie. It tells you they have to be the same. Okay? Now, if we look at our interval that we've created, so our interval is 824.2 all the way up to 1,775.8, okay? And we can see 0 is not inside this interval. Okay, 0 is not inside that interval. 0, if you're looking at a number line, all right, here's like 824.2. Here's 1,775.8. 0 is all the way over there to the left. It's not contained inside this interval right here. And because it's not contained inside this interval, let me write this sentence out. Because 0 is not inside our interval, we can conclude that there is a difference in the average miles to wear out for the two types of tires. All right, so let me get out my little highlighter here because this is important stuff here. We can conclude there is a difference. Okay? Now, let me go over that just one more time, okay? First thing, if the tires were the same, then we would say mu1 minus mu2 has to equal 0. And then all I did is to kind of wrap my head around it. I said, well, I'm going to use basic algebra. I'm going to add mu2 to both sides. And I find that mu1 equals mu2 if they are the same. Okay? Now, next we looked at our interval that we created. So our interval was 824.2 for a lower limit, upper limit's 1,775.8. 0 is not inside that interval. Therefore, I know there's a difference between these two tires. Okay, there's a difference. So what this confidence interval has allowed, or what it's done, is now we can make a decision about the equality of these two population means. Okay? We know they're different. Now, this isn't going to tell me what tire is better. Okay? That's going to be up to you. What I would do to figure out what tire is better is I'd come all the way back up to here and say, okay, well, we only collected information on 100 tires. The more tires that we get, the better approximations we're going to have. Remember, large sample sizes dictate everything. So if you can get a better or larger sample size, then you're going to figure out, okay, who has a better tire? And remember, you don't want tires to vary. Like if you look at tire 2, although, if you look at these two means, they're really not that different. 26,000 miles and 25,000 miles. I mean, the difference between these two is 1,300. We can see that right here where I just put these stars. I mean, it's really not that different. However, those variances are very different. One is 1.4 million. The other is 1.9 million. I mean, if you were to round those to the nearest million, think about that. If you were to round these variances to the nearest million, I'm going to write this in red. If I round to the nearest million, that's 1 million, and this is 2 million. That's a big difference. The variance is huge. So remember, you want a nice bell-shaped curve. And the better bell-shaped curve you can get, the better approximation you're going to have and the better decision you can make in terms of whatever you're studying. Okay? So this is basically going to sum up section 3. Or I'm sorry, what is this? I don't even remember what section it is. Section 4. Okay? Every single problem is done the same exact way. You just follow how you make your best point estimate. You find your standard error. You use that information to calculate your confidence interval. And then now what we can do is we can make decisions. Remember, if there is a difference, 0 will not be inside the interval. This means there is a difference. Okay? If you calculate a confidence interval and 0 is inside it, then these two population means are they're the same. There's nothing different between them. Although your statistics that you've calculated may be a little bit different, these two populations means are essentially the same. Okay? So good luck with section 4. And in section 5, I'm going to be honest with you, it's the same thing. It's just we're not talking about population means. We're going to be talking about the difference between two binomial proportions. So we're going to be talking about P hat, Q hat, and P and stuff like that. So I'll see you in the next video. It's going to be very similar to this one. Talk to you later, I guess.